convolution is just about one of the most confusing things out there when learning about signals and systems. In fact, it's literally in the name. It's so convoluted. And if you were to Google what is convolution, you'd be met with perhaps some description of merging the shapes of two functions together, and then you'll see a wall of maths. Now, I'm not saying the maths is wrong, it's just not easy to understand intuitively. And that's the goal for today's video. Today, I'm going to try and explain through the use of an analogy what is the intuition behind convolution. And my analogy involves fire, or well, at least smoke. So let's step outside to do this one. So imagine it's New Year's Eve or something and there's just loads of fireworks going off. And our goal is to figure out at the end of the day how much smoke is in the air because of all these fireworks. So to illustrate, let me use matchsticks as an example because, well, I can't set off any fireworks out here. So first, let's start by defining what I'm going to be calling the smoke function. And that is the function that describes when I set off a single firework, how much smoke is in the air because of that one firework. And we might imagine that it looks like some sort of exponential decay like this. So initially, we have the max amount of smoke in the air, but as time progresses and the smoke dissipates, well, the smoke in the air decreases. And the next function we're going to be looking at is called the fireworks function. And that basically just says how many fireworks are we setting off each minute. So if we're trying to figure out how much smoke is at the end of a certain time frame after, say, 5 minutes, well, it should make sense that we have to somehow cumulatively add up the amount of fireworks that we're setting off each minute combined with each firework's smoke function to figure out how much smoke is in the air at the end of 5 minutes. But how do we do this mathematically? Well, let's start by looking at this minute by minute. So at minute 0, let's just say that we are setting off one firework. So that means f of 0 is equal to 1. So just one firework at minute 0. So how much smoke is in the air at minute 0? Well, it should make sense that we just multiply f of 0, which is 1, times the smoke function of 0. That gives us the amount of smoke at the start of minute 0. All right, so what about minute 1 then? Let's just say that f of 1 is equal to 2. So at minute 1, we're setting off not 1, but 2 fireworks. So at minute 1, we have 2 fireworks. Now, the amount of smoke at minute 1 should just be f of 0, the previous minute's fireworks, times s of 1, because those previous fireworks have had 1 minute to dissipate, plus the newly created smoke, f of 1 times s of 0. All right, so now let's go on to minute 2. How much smoke is there at minute 2? Well, if you can notice the pattern, it should be just f of 0 times s of 2, plus f of 1 times s of 1, plus f of 2, the newly created smoke at minute 2, times s of 0. And of course, we can extend this to any arbitrary time frame. So let's look at minute 5, for example. At minute 5, we have f of 0 times s of 5. That's how much smoke is left over from the first round of fireworks, plus f of 1 times s of 4, plus f of 2 times s of 3, plus f of 3 times s of 2, plus f of 4 times s of 1, and finally plus the newly created smoke at minute 5, which is f of 5 times s of 0. And this should make intuitive sense that the amount of smoke left over at the end of any arbitrary time frame is just the sum of these contributions from the newly created fireworks at each minute. So mathematically, what we've done is we have convolved these two functions. We have convolved the fireworks function f and the smoke function s. And to put this mathematically, well, it looks something like this. Of course, since fireworks are discrete events, we either set off a firework or we don't, well, this is a discrete summation. But of course, we can extend this to a continuous function as well, such as maybe the voltage across the capacitor. But instead of a discrete summation, we turn this into a continuous integral over a certain time frame. And this is called the convolution integral. All it's doing is it's keeping track of the running contributions from the product of these two functions as time progresses. And this is over a time period t. You should note that the other variable here, tau, is just a dummy variable used for the integral. It's the equivalent of I in the discrete summation case. So I hope that fireworks analogy gives you some understanding as to what convolution really is. And the way I would personally describe it is when you convolve two functions, you're basically combining them in such a way that tracks their interaction throughout time. And well, if that fireworks example didn't quite stick with you, here's another one. When I'm talking to you right now, you don't just hear the sounds that I'm making right now. You're hearing a combination of those sounds as well as the previous sounds that I've made as they echo throughout the room and eventually make their way to the microphone. So in a sense, you're hearing the convolution of two functions. One function is a function that describes the sounds I'm making over time, and another function is one that describes how those sounds echo throughout the room and eventually hit the microphone. So my goal of this video really wasn't to dive into the mathematics behind convolution. In fact, there are loads of videos that already do that. But I don't feel like there are very many videos that explain the intuition behind what convolution is. And well, there's no use memorizing a bunch of formulas if you don't understand what they're doing. I mean, sure, you might be able to pass an exam, but you'd never be able to actually understand what they're doing and apply them in the real world. So I hope that was useful to you guys, and if you like videos like this, please do subscribe, and I'll catch you guys next time.